Hi, my name is Chen Chao. Today, I want to introduce my final project of applied deep learning course. So I will make a presentation to talk about my project in a high level. My presentation will be divided into 4 parts. First, I will introduce the overall background of this project. Second, I will introduce how I read raw data and how I preprocess the data to get the input needed to train the model. Third, I will introduce what my model is, and finally, I will discuss how I predict and how I evaluate the performance of my model. So first, the goal of this project is to reproduce the method and result presented in the paper detecting cancer metastasis on gigapixel pathology images. And we can see from the paper that the motivation of this method is that manual search for tumor cells requires highly skilled pathologists and is time-consuming and error-prone. In contrast, computer-assisted detection of lymph node metastasis could increase the sensitivity, speed, and the consistency of metastasis detection. Now, let's talk about data preprocessing. Let me first describe our data. So my data are all tumor images from Chameleon 16 dataset. There are also corresponding tumor masks that tell us where the tumor cells locate. For this project, we have 22 gigapixel pathology site images and 21 corresponding masks. So I found out that the number 38 should be removed from our dataset because it does not have corresponding tumor mask. To open the TIF file, I install OpenSlide in Colab and use OpenSlide API to read all slides and masks. By using OpenSlide API, we can also access to different zoom levels of the same image. So here we can see the sample data of tumor images and mask. The figure 1 is a slide image, figure 2 is mask image, and figure 3 is a combined figure that merges slide image and mask images to more clearly shown well those tumor cells located in the original image. Then let me talk about the pipeline. First, I need to do chain test split using remaining 21 slides images and their corresponding masks. We randomly select 2 pairs of images and masks for validation, 3 pairs of image and masks for testing, and the remaining 16 pairs of images and masks for training. Then we create patches from training and validation set. The generated patches are squares and should have shape 299 times 299 for both zoom level 1 and zoom level 0. After that, we identify the center region with shape 128 times 128 and check whether there exists at least 1 tumor pixels in this area. If there exists, I label the patch as tumor, otherwise I label it as normal. And moreover, since tumor pixels are much less than normal pixels for sure, I designed the algorithm to select those 2 pixels with equal chance so that we will get balanced training data. Then I ignore non-tissue areas of the slide by looking for all gray regions as well. Also, I ignore patches without many tissues. I set the threshold to 30% so that the patch can be stored only if the patch has tissue percentage larger than 30% of the area. For the modeling part, I use transfer learning for this project. I use pre-trained Inception V3 model with weights on ImageNet. Also, I concatenate activations from level 0 and level 1, training patches to make joint prediction. Then I use dense layers and dropout method to improve model performance. So here's the model. And finally, I predict the tumor cells from testing set and make some evaluation on how well my model performs on unseen data. So I need to first segment testing images to small patches row by row and column by column. Then I use the model with best validation accuracy saved during training process to make prediction for each patches in testing set. After that, I show the exact position of predict tumor pixels in the original slide images and present the prediction result in a heat map. And here we can see the accuracy plot and the loss plot of my model. The model performs well on validation set. And the final step is to exhibit related matrices to show the model performance. I use precision, recall, F1 score, and AUC. As we can see for slide 19.1, all of the matrices looks good, but for slide number 75, AUC is still pretty high, but precision, recall, and F1 score are all relatively low. But from the heat map, you can see that our model can roughly capture the distribution of tumor cells in the original image. It is still meaningful in realistic condition in my mind. So that's all for my PowerPoint. And then let's go through the code of the final project and see how I implement this method. So first, I download OpenStar API and import as many libraries as we want. Then I get all of the path name of the images saved in my Google Drive. And that includes both slide images and mask images. And then I check whether I can open all slides and dump sample them correctly. And then I show the last 3 images with masks to check the reslide function and see how our data look like. And next, I use the random API to randomly split data. I first sample 5 from the whole image path. Then I sample 2 from these 5 passes, names as validation images paths, and the remaining 3 as testing image paths. Then I go into the patch generation part. There are a few essential functions. First, I use the center checker function to check whether tumor exists in the center of a patch. Then I use the normal tumor tissue detection function to help me differentiate tumor pixels and normal pixels. And inside this function, I crop image to make sure we can always get a patch starting from any XY axis, which will be generated randomly in the patch generation function. And then I also improve the efficiency by using tissue, so that we will ignore those non-tissue areas. Then I use get patch function to get a patch for both tumor image and the mask. Then I combine all of the functions above to successfully generate patches from training and testing dataset. Then I will save all of the train set and the validation set to my Google Drive so that I can access them later. And then for the modeling part, here I build the multi-resolution model using Inception V3 model on ImageNet. And I also use data augmentation to improve the accuracy. Then I plot the loss and accuracy curve using the function given by the professor in homework 1. Then for prediction part, I use model.predict and the data processing to get the predict result. Finally, I generate prediction heat map along with matrices AUC, precision, recall, and advanced score to show my model performance. Okay, so that's all for my video. Thank you.